Mr. P Singh for your presentation.
Can you enlarge this?
Good afternoon. I'm going to give a very simple overview of what we see and how we see, giving you in the context of supermassive black holes. So far, what you heard about black holes being built by gravitational collapse, supermassive black holes are much more of an enigma, and actually nobody knows how they are formed. But we see them, we feel them, and so on. So my story will be more based on from observation point of view and the simple or possible explanation that one can provide for that. So actually, this black holes were first discovered by simple use of Kepler's laws. Okay, you felt there was some invisible object tugging around on the star and making it move in a certain way that required a large amount of mass. And actually, it was only till 71, although they were seen as very prolific, very prodigious X-ray producers, very hot objects. They were not detected in constellation Cygnus and just named as the first X-ray source, Cygnus X-1. This is the beginning of X-ray astronomy. But the radial velocity measurements and finding the optical counterpart took some years, and only in 71 they realized that no, this has to be a very massive object. But these are all solar mass black holes. Okay, in the sense they are at the most around 20 solar mass. Nobody till today knows how to make a black hole which is more massive than 20 solar mass. And maybe the gravitational wave, which is showing that the black holes can merge and produce larger black holes, maybe that process takes us to these billion solar mass black holes that I will be talking about. Okay. So in fact, the existence of such thing was indirectly known by Carl Seifert when he discovered so-called Seifert galaxies, which are about 1% of all galaxies, which are very active and so on. They have a star-like nucleus. He was studying the spectrum, and he found that they do not have the star-like spectrum, that they look like stars, and they are extremely bright. They are like that central object in the nucleus of a galaxy is about thousands of times brighter than the entire galaxy put together. And where is that energy coming from? So, and this name then slowly appeared. There is an active nucleus of the galaxy and so on, but only when radio astronomers started observing the universe in late 60s, that people started to hypothesize what we call putatives for mass spectrometry, to believe that some things like this exist, but we cannot see them and so on. Okay? So I can't help showing this slide because we worked for almost 30% of my life, and still counting, and built India's first telescope. And this is a multi-wavelength satellite which is operating today since September 2015. It's a national and international observatory. Anybody can go and observe with it. And it actually has a lot of international, subscription and so on. And the uniqueness is that we put together a very large band of X-ray instruments from medium energy, soft X-ray, hard X-ray, and 2 ultraviolet telescopes with multi-institutional collaboration and so on. So, I can tell you that doing blue skies, science is not that easy. It requires a lot of technology to go on. And now we've seen these observations. Okay, this is actually an image by ultraviolet telescope of the same one of the Seifert galaxies that Seifert had discovered in 1943 and so on. It goes by the name of NGC 4151, which is just a catalog number, New General Catalog. And you have and you see the very bright nucleus and so on in the near ultraviolet and then in the far ultraviolet and so on. These are the kind of images our astrosat is producing on a regular basis, and for anybody who wants to use it. And the same galaxy now, I'll show a multi-wavelength picture. This is blue is the X-ray and the red is the radio. Okay, so now I put together, you see that the brightness in the center is all X-rays, and the around there is a ring of radio emission and so on. And then you have these such objects where you have these white dots are the optical, and you have the radio in blue, and this purple is again X-ray. Again, you see there is a concentration mostly in the X-ray in the center, and so on. This is a 1.9, this radio galaxy. Then becomes what we call quasars, and which are even further away, and so on. And you see that the galaxy is no longer visible, okay? And only the nucleus is seen. And you have these jets, the jets that you saw here. Now you see the jet also in X-ray. So it shows you this movie, the famous Messier 87, which is a French astronomer in 1800 and so on, who made the first catalogue of galaxies. And this is a part of the sky where there are lots of galaxies known as Virgo Cluster. It is spread over tens of degrees on the sky and so on. And when you go there, right in the middle, you will see where N27 actually is. Okay, and why it is such an important thing to study, because we know there is a black hole, there is a very bright object. So we are still seeing light. You're not seeing the hole, right? And so on. So you suddenly see there is a jet will appear, and you go closer and closer. There it is. Okay. So, and people have imaged this. So this was a target. This was the target of the Event Horizon Telescope that people have talked about and shown you pictures. And I show you how and what are the sizes involved, basically, and so on. Now, this extragalactic jet that is coming is being fueled and ejected from close to a monster black of 3 billion solar mass or something. Okay, you don't know how the 3 billion solar mass is produced, but this is what we believe, that we require this much mass. Let me show you why. And there is a disk around the spinning black hole, because the angular momentum has to be conserved. So all the matter that is swirling around actually forms a disk, and that disk plays a very important role again when you see the images that were found in radio astronomy called the Event Horizon Telescope. And these particles, along with radiation, then they flow rapidly away from the black hole along the magnetic field lines, producing jets and so on. And again, the black hole is probably not stationary, most likely it is not, and it is spinning very, very rapidly, again to conserve the angular momentum. Whatever goes in, and as it gets closer and closer, it spins faster and faster. So this was the artist's impression of what we have. There is a disk and there is a jet. And that is what is probably at the center of the zone, but it was not imaged till 2007. So why we say there is a supermassive black hole? There is a very simple argument that there is a regulation of the radiation that can be produced by a given body of mass. Okay, of a certain mass, and that goes by the name of a Eddington limit. That the radiation pressure should be balanced by the amount, the radiation cannot be so large that it blows away the star or the object that you have. So it is balanced by the amount of scattering, Thomson scattering and so on, and that is going to the, so you have to have some minimum mass to produce certain energy. So if you see a very bright object like in the AGM, or the active galactic nuclei, which is what we measure in terms of ergs per second, 10 to 44, which is like 100 billion times more than our sun. Okay, and the mass has to be around this much. This is basically the lower limit, and that's why I say, but it is not seen. It is so small, so tiny. So the sizes are important. Okay, how do we get the sizes observationally? So that is what is the very simple argument. You see a very bright, very small object, and then you say, well, it has to be a black hole, which can only produce that much heat, energy, and so on. Okay. Though, just to recap, that was a very simple argument without getting into the Einstein theory of gravitation and so on. What would be the mass required and the radius required if the escape velocity were to be the velocity of light? Okay. So you do that, you will find that simple argument gives you what we call Schwarzschild radius, and which came through the general theory of relativity in a more rigorous way. But it is very easy to see what is the Schwarzschild radius is by simple argument of a Newtonian theory and so on. So any object whose radius is smaller than the Schwarzschild radius, we call it a black hole. The surface at the Schwarzschild radius, that acts as the event horizon. Okay, and which is valid mostly for a non-rotating black body. I'll tell you what happens in a black body, in a rotating black hole, which is slightly different. So neither light nor particles can escape through this surface, and that is why we call it black. So, okay, we can classify them based on the Schwarzschild radius and so on. You see the radius is linearly related to the mass, while the enclosed volume corresponds to third power. And now this Nestor 87 with the mass of 10 to 9 sun is actually Schwarzschild radius of 10 to 10 kilometers, which leads to a very, very small density. Actually, it is less than the density of the star. Okay, and that when you go on to the center of a Milky Way, we have an object called Sagittarius A, which is in the Sagittarius constellation, and the radio astronomers give ABC, like X-ray astronomer gives 1, 2, 3, and so on. And then you see that now we are about 1,000 times more than the density of the water. And then sun, this is more than the nuclear matter, okay? But the size will have to be 3 kilometers. If you the Earth, you have to be condensed into a black hole, it will be a size of a 9 millimeter with enormous density and so on, okay? So I just want to put these numbers into perspective. I'm observational guy, so I like these putting numbers and so on, and this is what this Schwarzschild density is. So these stellar mass black holes have large densities, and those are the ones that we know they form in supernova remnants, explosion of very massive star when matter is crushed down to some very high density. Nobody knows what happens here and how they are formed. So just a simple arguments, as the body accumulates matter, its Schwarzschild radius will increase more quickly than its physical radius, and that at a certain time we call it a supermassive black hole, and they do not really form from a singular collapse or even a collapse of clusters of stars. They are probably formed as we saw in the gravity wave phenomena, but that will also require billions of stars to collapse even for that. So they may begin life as smaller and then grow, and that is where the accretion of matter, which also gives rise to the energy and the prodigious amount of light that you see comes about, so on. So where did astrosat come in? In astrosat, I showed you this image. This is another galaxy. What we are able to measure in this X-ray, ultraviolet, and UV, because we have this niche area that we are looking at all these wavelengths simultaneously. All the instruments are pointing in the same direction on the satellite. We can actually measure how the time intensity varies with time. So you see there is almost a factor of 2 variation in the X-ray, okay, in the soft X-ray, and then it's only 25% and only 15% in the UV and UV. So if the light, the entire body has to participate in the emission, it's needed to produce a variation of factor of 2 and 3. This requires a very, very compact object, because the light should be able to travel across that much distance that quickly within a few light days. Okay, this is just a 4-day observation, and that is another strength of astrosat. You can keep looking and staring at one part of the sky for a long time, which other observatories will not do, because a lot of competition from non-black hole, and other people and so on. So now where these radiations come from, as Kipthon actually showed in one of the books 40 years ago, that the disk which forms around because of the angular momentum conservation is actually produces ultraviolet light and so on. What he did not put in that time, which was later discovered, was that there is also a huge amount of X-ray emission, which is shown as a yellow here and so on. And there is a lot of interaction between these emissions. For example, is the ultraviolet emission getting reprocessed through accretion and producing the X-ray upscattered through Compton scattering, or the X-rays are reflecting off the disk and then getting reprocessed and so on. So what you can do is do the cross-correlation studies and find out the lags between these timings and so on of this emission. That's what we do, and we are finding that, for example, the ultraviolet is lagging behind, and therefore there's evidence for processing in the accretion disk of X-rays into UV. So on, opposite is also true. So this is the diversity of the kind of emission process in black hole interaction taking place. How is the mass coming in? How is it going into the luminosity and so on? And this is the case where it is opposite. There is another galaxy and so on. Okay, and these things actually give us limit on the mass of the black hole. And you see there are million. These are what we call as small intermediate mass black holes and so on. Okay. Now, other important things before we go to the Event Horizon Telescope. I'll leave that to set behind now. And there are other orbits for the matter going around the disk. One of them is known as the innermost stable circular orbit, or ISCO. And this is where a test particle can stably orbit a massive object in general relativity, so on. The location depends on the angular momentum of the central object, and therefore non-rotating Schwarzschild black hole. The gravitational field can be expressed with the Schwarzschild matrix, and it is 3 times the RS. That means the particles cannot go closer than 3 times the Schwarzschild radius. Okay, so that is one size that you have. So on. That this plays a very important part up to what size the accretion disk can approach, because that is composed of ions and particles and electrons and so on, the gas. So that cannot come closer than 3 Schwarzschild radius. Now there is another effect, simple special relativity, without going to general relativity, that the light bends when you go from moving frame to stationary frame, moving at a certain angle. So the light very close to the black hole, near ISCO and so on, can actually bend. So the light coming from the accretion disk can actually come and look like a ring, and that's what will happen when you see. So a spherical region of space where gravity is strong enough that photons, which are massless light, they are forced to travel in orbits instead of straight lines. Even they are forced to travel, and that is of course general theory of relativity. And these proton spheres exist around the black holes up to this. You can see them here. What happens to the photon trajectories and so on, and they can come up to 1.5 Schwarzschild radius closer. Okay, and that we call the photon sphere. Okay, so this is what you can look, because we are always seeing light. You know, we cannot see dark, right? Black is black. So what is we are seeing is always with light. Okay, some light, radio, X-ray, UV, and so on. And then there are these spinning black holes, which are named after a New Zealand astronomer, Kerr. They call it Kerr black hole. And he emphasized that you have this event horizon, then you have the photon sphere, and so on, which is 1.5 times. And then there is something called the ergosphere, from which you can actually extract energy and produce those jets, so on. So as it rotates, it twists space-time in the direction of the rotation of the speed. So actually these people, Event Horizon, are able to tell you whether the black hole is rotating clockwise or counterclockwise based on this. So this is what is also known as lens stream effect or frame dragging, and not getting to those equation and details. And this is how it is possible to extract energy out and power the jets and so on. Greek word airborne meaning work. Okay, is based on. So this is the picture. This is what Event Horizon Telescope wanted to do. First, having selected a particular object which is not too far. Okay, and M87 is the nearest cluster and probably also the nearest supermassive black hole, and that was selected. And I showed you the picture of that. And you have the Event Horizon. There is somewhere singularity here, and then there is a photon sphere and so on. And there is a huge amount of jet that we saw in the animation and so on. Now, how did you get to such small sizes? Okay, these are very, very small sizes. I showed you this is like a few kilometers, a few hundreds of kilometers, a few light days that you can go down at billions of light years away. Okay, so which is actually 55 million light years away. This galaxy, and the roughly this is the translation. Want to go into kilometers, and the size of the photosphere is only 10 to 10. Okay, so there is an order of 10 orders of magnitude difference in size. So this will be 15 micro arc seconds. Now 15 micro arc second imaging means that you should be able to see a rupee coin from a geosynchronous satellite and so on. Okay, so this thing also showed that okay, maybe it is not the mode calculation should be 20 to 40, so you need high resolution. This is just actually a simulated image, not the real image. And so the radio telescopes were used. Okay. And the resolution in a very simple undergraduate physics will tell you it is lambda by d in radians is the resolution required. So you can either go to very the short lambda or increase the d large. But then you cannot make dishes more than 100 meter size and so on, and that will lead you to 20 arc-second, your orders of magnitude away. So you have to go to very small wavelengths, but the small wavelengths are limited by our atmosphere. So you need a large aperture. This is what they did, what is called aperture synthesis. They actually put together all the telescopes from the North Pole to the South Pole and all the in-between, and then created this 11,000 kilometer size radio telescope, okay, and which will have the resolution of about 25 micro arc second. And remember, this is a millimeter, or gigahertz, the kind of frequency that you used to be in the radio TV programs and so on. So this is the image, actual image that they saw, and a bright ring with a central dark area, similar to the long predicted structure of optical thin emission from a hot plasma surrounding a black hole. So what you see is a emission from the disk, which has been bent to look like a ring. So this is probably the photon ring that we are seeing, okay, and people call it the shadow of the black hole. You can give it different names and so on. And this is from the estimate, people have done lots of calculations, lots of simulations. That's why it took almost a year to get this data out. And they found that we can actually explain a lot of things about this particular black hole, that it is actually now well measured mass. The diameter is well measured, which is roughly 270 times the Earth-Sun distance, okay, and that is as expected by Yuan and Ramesh Narayan, who was from Raman Research Institute before he went to CFA Harvard. And the flux density also implies what is the accretion rate going in, and I leave you with this picture showing where the Pluto is, where the Sun is in this image, and where the Voyager is placed.